Okay, so in Chapter 5, we are going to start talking about what we call z-scores. And z-scores are a way to make our data uniform so we can compare it against different types of data sets. So they don't always have to be on the same scale. So I could compare maybe employee ratings and salaries, which are on two different scales. I can compare them together and talk about if something is significant or not. So let's start just talking about what z-scores are. And they are precise locations for each x value on what we typically do as a normal distribution, which is your bell-shaped curve. Z-scores can be positive or negative, depending on if they fall above or below the mean. So obviously positive z-scores fall above the mean, negative scores fall below the mean. A z-score of 0 is the mean, okay? So basically, instead of having like a mean of 12, you're recalculating so that your mean is a 0. So typically our z-scores fall anywhere between -4 and +4. We don't really, I mean, you can go outside of that, but it's very, very rare for that to happen. Most of the time, they're going to stay between -4 and +4. Actually, most of the time, they'll probably stay between -3 and +3, but there are some extreme cases. The z-score indicates how many standard deviations a value is from the mean. So we've been talking about standard deviations in the previous lesson, in the previous chapter. Now we're actually talking about uniforming them so that we know exactly what one standard deviation is or what two standard deviations are. So the z-score is going to give us that information. And then here is the actual formula. So the z equals the x, or the data value, minus the mean divided by the standard deviation. So you need to be able to know the mean and the standard deviation in order to find a z-score. And when we talk about z-scores, we are always talking about populations, not samples. Notice we're using the mu, or the funky looking u, and then we're using our standard deviation, our population standard deviation, not our sample. We will eventually talk about how to do this with samples as well. Okay. So here's our standard normal distribution, okay? This is our nice, pretty bell-shaped curve. One of the things I need you to understand is between all of these dashed lines is one standard deviation, okay? This center solid line, that is our mean. Okay, so if I go out to this first dashed line here, this is one standard deviation away from my mean. Notice that my z-score down here is 1. If I go to the second line, that's 2 standard deviations from my mean. Notice my z-score is 2. I can go the opposite direction as well. Again, starting at my mean, coming back, I've got -1 standard deviation from my mean, which corresponds to a z-score of -1. Also notice that from 0, or from my mean, to -1 standard deviation, that is 34.13% of my data is expected to live within this. Okay, so that means that if I take these two values and add them together, I expect that 68% of my data lives between -1 standard deviation and +1 standard deviation from my mean. Okay, so the large portion of your data. Now let's look at from -2 to +2. So that's 2 standard deviations away from my data. We would expect 95% of our information or our data to lie within 2 standard deviations of our mean. Okay, and then if we go out 3 standard deviations, we expect 99% of our data to lie within 3 standard deviations of our mean. What that basically means is that if we find a z-score and our z-score is typically above the number 2, that's probably pretty significant. That's a pretty good distance from our mean, because we expect that 95% lies less than 2, from -2 to +2. So if I have a z-score greater than 2, there's only a 5% chance that that's going to happen, because that's the distance on the other side of that. The same thing with a 3. From -3 to +3, we expect 99% of our data to live within 3 standard deviations of our mean, which means that anything outside of that, there's only a 1% chance that it's going to actually be outside of that value. The other thing you have to understand is that 50% of our data is expected to live above our mean, and 50%, 50% of our data should be living below the mean. Our mean should be our halfway. Remember that our normal distribution is a nice, pretty, bell-shaped, symmetric distribution. So half of our data lives on one side, half of our data lives on the other. That's another thing that the z-scores do for us, is that we call it normalizing our data. So we're basically trying to fit our data into this nice, pretty, bell-shaped curve. All right, so there's our z-scores. Again, that's the mean, the data point minus the mean divided by the standard deviation. So let's do a few examples of calculating this. We're going to do examples where I'm going to give you the mean and the standard deviation, although you could be asked to do it from a data set. So it is possible to find the z-score, but having to find the mean and the standard deviation first, but not today. So we're going to just compute some z-scores. So our first example here is we have a mean of 65, a standard deviation of 20, and we want to figure out what the z-score is for the value 40. Okay, so again, we have our x minus our mean divided by our standard deviation. So in this case, that would be 40 minus 65 divided by 20. And that would give us negative 25 divided by 20. Which would give us a negative 1.25. So that is negative 1.25 standard deviations away from our mean. So you can see I've got us a standard normal distribution. I just want you to kind of see where that is on the graph. So if I draw my line here, that would be just about a fourth of the way between negative 1 and negative 2. So there's my red line that identifies that negative 1.25. So now let's do another example. This time our mean is going to be 15, our standard deviation is 2, and our x is 22. Again, we're going to do that same value, x minus our mean divided by our standard deviation. So we get 22 minus 15 divided by 2, which is 7 divided by 2, which ends up being 3.5. That is pretty far out there. That's halfway between 3 and 4 on our positive scale. So if we put it, maybe it's right back there at 3.5, way down here at the end of our z curve. Now, one of the benefits of the standard curve is that it allows us to look at these two data points on the same curve, because they're not the same values. The means and the standard deviations are definitely different for these two values, and if I'd have looked at these, I might not have thought that 22 was that big of a difference from 15. It's only seven scores away, but with it such a small standard deviation of only 2, that 7 points was actually quite significant, giving us that 3.5. Okay, so that, again, that's one of the benefits of computing a z-score versus just looking at the standard deviation and a point, because you can actually see how far away is this point from my mean or from my 0 value. And then I can use really big numbers, so we can say that my mean is 12,000, my standard deviation is 2,000, and I want to look at a point of 10,750. And the really cool thing is my z-score is going to convert that into something I can put on my standard normal distribution over here and compare to the other two we've already calculated. So again, we're just doing the x minus the mean divided by the standard deviation. So we've got 10,750 minus 12,000 divided by 2,000. So it's going to be 1,250, a negative 1,250 divided by 2,000, which would give us a negative 0.63. So this is going to be on that negative side, not quite to negative 1, maybe about right there on our graph. And we get this negative 0.63. And again, it allows us, I mean, obviously the mean and the standard deviation for this guy was much different from the first and second example. So we can see that even though the mean and the standard deviation are very, very different, we can still compare their z-scores to each other. And that's one of the benefits of using a z-score, is being able to compare data to other data sets that are on a different scale than what you're looking at. So, and you get to put it all on one normal distribution. I hope this helped you with computing z-scores. Let me know if you have any questions.